Alright, so question 1. We have to compute the directional derivative. Since the function is defined in two different ways, it has a different behavior in the origin than in the rest of the plane. In here we will have to use the definition of the directional derivative. So the duf in the origin, this is what we have to compute. We just have to use the definition. So that's the limit for h to 0 of the f of hu1 hu2 minus the f in the origin divided by h. Alright, now we can start plugging in things. So we get the limit for h to 0. So in the f of hu1, hu2, remember h is non-zero, so hu1 and hu2 is not the origin because u is a unit vector, therefore u1 and u2 are not both 0 at the same time. Therefore we can plug it into the formula of the exercise. So what we get is, I replace x by hu1, so we get, let's write it like this, hu1 squared times hu2. F of the origin is given that it's 0 over there, so that's 0. And then we divide by h. Okay, sorry, I forgot the denominator. The denominator is x to the 4th, so that it's hu1 to the power 4 plus y squared, which is hu2 squared. Okay, and now we can, then we have to divide by 1 over h. Divide by h, sorry. So we have a 1 over h there. Now let us simplify a little bit. So we get 1 over h. Here we get h to the 3rd u1 squared u2. And in the denominator we have h to the 4th u1 to the 4th plus h squared u2 squared. Okay, so we can take this h together, and so we can cancel a factor h to the 3rd. Remember, when taking a limit, h is not 0, so we can cancel out these terms because we're not cancelling at 0. So what we get is u1 squared u2 divided by h squared u1 squared, u1 to the 4th, plus u2 squared. Okay, so at this point what most of you did, I will write it down, it's not correct, is argue as follows. Well, we can just plug in this limit, we can just plug in h equal to 0, and then we get the following. We get, then we have u2 cancels with u2 over there, so we get u1 squared over u2. Of course, we can immediately see that this is not correct because here, let's change the color. We have a u2 in the denominator, and we have to be very careful with that because we don't know what the unit vector u is. But let's make a little picture here. Let's say over here. Unit vectors are all in the unit circle, so they might be over here. The problem is that u2 might be 0, right? That's the second coordinate. So for instance, if I'm one of these 2 points, which is the point 1, 0, and the point -1, 0, both of them are unit vectors, and for both of them it holds that the second coordinate is 0, namely the u2 coordinate. And then we have something that doesn't make sense. You see, like all major religions, mathematics has a number of cardinal sins, and one of the cardinal sins is that we can never divide by 0. So this is not allowed because we are dividing by 0 sometimes, right? So all of this is correct if we assume that u2 is not 0. So here we see that we really have to consider 2 different cases, namely the case where the u2 is not 0. Then the valid argument here is that this function over here is a continuous function of h everywhere. It's defined for every h, and therefore to evaluate the limit we can just plug in h equals to 0. But if u2 is equal to 0, this argument is no longer valid because now this function is not defined for h equal to 0, because we, as I just said, we may never divide by 0. That's absolutely forbidden. So in these kinds of situations, when we should just treat it separately, and when u2 is 0, well, we can see then that if u2 is equal to 0, then this is going to be 0, so the numerator is 0, the denominator is not 0, because if u2 is 0, u1 is not equal to 0. So then this limit is just going to be equal to 0. Therefore, in the case where u2 equals 0, we just get 0. And that is the final answer, and important is always make sure you're not dividing by 0, and if you're possibly dividing by 0 because there are some variables, you will have to split up the cases of this variable, in this case the case for u2. We have to split it up in the case where u2 is 0 or where u2 is not equal to 0. And that is the final answer. On to question 2 is we have to show that f is not continuous at the origin. Okay, so there are a couple of ways of doing it, and I will present one way and then I will explain how to do it in a different way. So first we're going to do it by contradiction, so we're going to assume that f is continuous. We're going to assume that f is continuous at the origin. And then we try to derive a contradiction. So what does it mean that f is continuous at the origin? So we're going to assume that the limit for the vector xy going to the origin of fxy is equal to f at the origin. Right? That is the definition of what it means to be continuous at a certain point. So important to know the definition here. Okay, so we assume this and we try to derive a contradiction. So first of all, f at the origin we know that that is equal to 0. Because that's how f is defined. So we're assuming this and we're trying to derive a contradiction. What we're going to do is use theorem 43, which says that if a limit is a certain value, then the limit along any path will also take the same value. So, for instance, if I take the following path, let's call it r bar of t is the path t squared, then according to theorem 43, right, just the goal that I'm working towards a contradiction, so I'm looking for a path that does not lead me, that leads me to a different limit. Well, according to theorem 43, this tells me that the limits along this path, f of r bar of t, okay, so first I have to check that this path is actually continuous and goes for the origin only for t is 0, but that's true, so you can check all these things yourself. And then this limit should be equal to, so what is the f of r of t? Well, you can check yourself if you plug this into the formula. So x is t and y is t squared, so I get t squared times t squared, I get t to the 4th. I divide by x to the 4th, which is t to the 4th, and y squared, which is also t to the 4th. So this is equal to, well, let's do one more step. I can just divide everything, so I get a half, and the limit of a constant is the constant itself. Yeah? Theorem 43 tells me that if the limit is 0, then the limit along every path is 0. But this is not true, because this is not equal to 0. Right? It's not 0. And it should be 0 according to theorem 43. Therefore, we have a contradiction. So, something that we assumed must not have been right, and that we assumed that f was continuous, so therefore f is not continuous at the origin. Okay, so that's one possible solution. Another solution that actually most of you took was to, you see, we have to show that f is not continuous, which means that the limit is not equal to 0. But it's enough to show that the limit doesn't exist, right? If the limit does not exist, it's definitely not equal to 0. So it's enough to show that the limit does not exist. And for this we can use theorem 45. Yeah, so the additional solution was to consider another path. For instance, r2 of t is this path. And then one can show that actually easier that the limit for t to 0 of f of R2 of t is equal to 0. Or you can also choose this one, 0t. There were a number of ones that you could have picked, or tt even. There were many paths along the limit was actually equal to 0. And now if we combine, let's take a different color. Let's use blue. Now we have this one and we have this one. So now we have two different paths along which we have two different limits. Then we can conclude by theorem 45 that the limit does not exist. And therefore we've also shown that f is not continuous at the origin. So that was the second solution. Most of you did the second solution. But the first solution is also fine. Both solutions are completely fine. Maybe I should write exactly what I mean. So the conclusion is going to be that the limit for x, y to the origin does not exist. And therefore f is not continuous at the origin. Okay, I'm writing it very abbreviated, but you see this is the structure of the argument where you're just proving that the limit doesn't exist and therefore that the function is not continuous at the origin. Alright. On to the third question, the second question. This was actually 1a and 1b, so let's now go to question 2. So let me first write the question. So we have the following function f, y, z, x, y, z is sine of x is equal to the sine of x, y, z. And we have to compute f, z, y. Okay, so this is a question that most of you did correctly. So first we have to differentiate with respect to z, because that's what the notation means. You can look in the lecture notes about that. So first differentiating with respect to z. Well, the derivative of the sine is the cosine, so we have the cosine. And then by the chain rule we have to differentiate what's inside. So we have to treat both x and y as a constant. So we have a constant times z, and the derivative of a constant times z is that constant. So that's always the first step. That will be the derivative of f, partial derivative of f with respect to z. And now the fzy is basically the dy of that thing over there, which is equal to, well, now we have a product of two functions and both functions depend on y. So now we should use the product rule. So first I have to take the derivative of the first term. So the derivative of the cosine is minus the sine. And obviously by the chain rule I have to differentiate x, y, z with respect to y, and then by the same argument as before this will give me xz. That's a dot. And then I have to multiply all of that, let's write some square brackets, by xy. So this is the derivative of the first term times the second term, plus, and now the first term times the derivative of the second term. Well, the derivative of xy, derivative with respect to y is equal to x by the same argument as before. So we can take one more simplification here. We have x squared yz. So we've got minus x squared yz sine xyz plus x cos xyz. And that finishes the exercise. Most of you, thankfully, were able to do this correctly. Alright, so now let me continue with the third exercise. We have to show by definition that a function, let's write the exercise again. So we have the function fxy equals 3x minus 2y squared. And we have to show it's differentiable at a certain point. So I will take my alpha to be 5. Your personal alpha is different, but you will see that the method is the same. So I'm going to look at differentiability at the point 8 minus 2. So I'm taking my alpha to be 5, but if it's different, you can yourself change the method of solution. Okay, so it has to be done with the definition. We've seen in lectures that it's usually easiest to use theorem 67, but here the question is to do it with the definition. So in the definition there are a couple of things that we need, namely the partial derivatives in the x and the y direction. So okay, let's first write down the EHK. So that's equal to the f of 8 plus h, right? That's the 8. The 8 is the first coordinate, and then we have minus 2 plus k minus the f in the point 8 minus 2. Sorry, I said 2 here. This should have been a minus 2, of course. Apologies. Then we have minus h f sub x in the point h minus 2 minus k fy in the point h minus 2, and all of that divided by the distance of the vector hk to the origin, which is the square root of h squared plus k squared. Okay, so there's a couple of things we need. We need the partial derivatives. So let's compute the partial derivatives. Let's do that over here. So, well, fx in the point xy is equal to, differentiating this to x will just give me 3. So that means that the fx in the point 8 minus 2, I replace x and y by 8 and minus 2, but I will still get 3, right? This is a constant function, it's always 3. The fy is equal to minus 4y. So the fy in the point 8 minus 2 is equal to minus 2 times minus 4, which is equal to 8. Okay. Why did I write a minus there? And then we need the function itself in the point. So f in the point 8 minus 2, that's equal to 24. Let's see, 24 minus 8, which is equal to 16. So it's always useful to start with computing this, and then we can just plug everything in. So let's do that. So the f of 8, the f of 8 plus h, comma, minus 2 plus k. So I replace x by 8 plus h, so I get 3 times 8 plus h, and then minus 2 times, and then we have minus 2 plus k squared. Right, then I subtract this thing over here, which was 16. Then I have minus 3 times h, because the 3 is equal to the f sub x in the point 8 minus 2, minus, that thing is 8, so minus 8k divided by h. Divided by the square root of h squared plus k squared. Okay, I'm going to run out of space soon. Anyway, so now let's simplify this a little bit. So, well, if we simplify everything, we get 24 plus 3h minus, let's see, we have k squared, we have minus 2k squared, we've got minus 4k times minus 2, so that's plus 8k. We've got 4 times minus 2, so we've got minus 8, minus 16, minus 3h, minus 8k over the square root of h squared plus k squared. Just using some algebra. Okay, well that's convenient because a lot of things cancel. We have 24 here, we have minus 8 minus 16, that cancels. Then we have plus 3h and we have minus 3h, that cancels. And we have a 8k and a minus 8k, all of that cancels. So all that survives is the minus 2k squared. Alright, so now let's continue on to the next slide. So what we are left with is minus 2k squared over the square root of h squared plus k squared. Let's write that down. Oops. Minus 2k squared over the square root of h squared plus k squared. Now what we have to do is to show the definition of differentiability means that the limit for hk going to the origin of this, of the absolute value of this, is 0, right? So let's write this over. Whoa. This is our goal, to show that the limit for hk to the origin of the absolute value of ehk is equal to 0. That's our goal. Okay. So almost always in these kinds of situations we want to use the squeeze theorem. So what we always can do is, since the absolute value is always positive, we can always bound it below by 0. And then what is this absolute value? This is a k squared, sorry. So what we get is we get 2k squared, because k squared is always positive and the absolute value of minus 2 is 2, divided by something that's also always positive. Okay. Now our goal is to turn this term over here into something that we can just, something that's continuous at the origin. So when evaluating the limit, we can plug in hk equal to 0, 0. So what we can do here is we can estimate k squared by k squared plus h squared. Right? Because k squared is positive and we add something positive. And the reason I'm doing this is that now k squared plus h squared cancels with the square root of k squared plus h squared. Well, it's actually equal to 2 times the square root of h squared plus k squared. Okay. And now we're in a prime position to apply the squeeze theorem, because the thing that we want in the middle is bounded below by 0 and bounded above by this. So now we can use the remark that since the limit of hk to the origin of the right hand side, which is 2 times the square root of h squared plus k squared, this is equal to 0. This follows by what we did in chapter 2, specifically the remark at the end of chapter 2. And it's also equal to the limits of the thing on the left hand side. We can now say by the squeeze theorem the limit of the middle will also go to 0. Now I'm running a little bit out of space, so let's continue in black. So f is differentiable. I will abbreviate this at the point 8 minus 2, because we verified this with the definition. Okay, so that finishes the proof. So one important remark is, let's maybe use this in blue. So what is wrong is the following, is that what many of you said is, well, we have this inequality, and now I'm going to take the limit in all 3 inequalities. So therefore, let's do it in blue. So this is wrong. Therefore, the limit of 0 is less or equal than the limit of ehk is less or equal than the limit of 2 times the square root of h squared plus k squared. Okay, but this is wrong. So you cannot conclude from a string of inequalities that the same inequality holds for the limits. This is not true, and I will illustrate this in the next slide. So what some of you want to use probably is something like this. We have that f is bounded below by g, which is bounded below by h, and then something about the limit. So I will not write everything. So this is what some of, or a lot of you actually try to use. Sorry, it's with the limit. And actually, so this is not quite what the squeeze theorem says, but there is one of the limit rules which is similar to this, but very important, there we already assume that all of the limits exist. So if we know that the limit of g exists, then this is valid. But in our exercise, remember, we're trying to prove that the limit of the absolute value of EHK is equal to 0. But we do not know yet whether the limit exists. Therefore, we cannot use this argument. We have to use the squeeze theorem. So please, so many of you made this mistake, so please, next time you have a question like this, train yourself to use it in the squeeze theorem and write it the way that I just wrote it. So first write the inequality, then say since the limit of the top thing is a certain value and the limit of the bottom thing is a certain value, by the squeeze theorem the limit of the middle thing is also that value. So it exists and it is equal to that value. That's an important remark that I wanted to mention because many of you made this mistake.